In this chapter, we will begin our study into chemistry, and we will cover some basic definitions first. Some of those you might be familiar with and some probably not, but we'll get started. First of all, let's look at some atomic and molecular perspective. Let's talk about what matter is. Matter is anything that has mass and occupies space. So anything around us, pretty much, even what appears to be empty space, is or contains matter. And matter is composed of atoms, and we will talk about what those are in subsequent slides. But matter, the definition that we're going to use, is anything that has mass and occupies space, so three-dimensionally. Mass, however, is a way to measure the amount of matter that is contained in an object. And we use mass and weight interchangeably, however, they are not the same thing. Weight is a force, and weight takes into account the acceleration due to gravity. So we have a certain weight. When we step on a scale, that's actually our weight and not just our mass. And weight is dependent on the gravity, the pull of gravity, so we weigh more on Earth than we do on the moon, for example. And our mass doesn't change, it's the same, because remember, a mass is measuring the amount of matter that is contained in our body, but our weight does change because the weight is dependent on the pull of gravity, and gravity is less on the moon as it is on Earth. So even though they're used interchangeably, they don't mean the same thing. So make sure that you kind of keep that straight in your head. Law of conservation of mass is a very fundamental law, not just in chemistry, but in other sciences as well. And it's very simply stated, it says that matter cannot be created nor destroyed. So we cannot make anything out of nothing, and we can't make something disappear necessarily, so cease to be. For example, if I have this reaction over here where I have hydrogen gas reacting with oxygen gas to produce water vapor, which is also a gas, it tells me two things, and this is the application in one of the applications in chemistry is based on chemical reactions. In a chemical reaction like this, what the law of conservation of mass tells us is that whatever I start out with on the left-hand side, so the elements that I start out with on one side have to appear on the other side. So if I have hydrogen here and oxygen on the left-hand side, I better have hydrogen and oxygen on the other side, the right-hand side as well, because otherwise that means that I have destroyed something. And another thing that it tells us in chemistry is that whatever we start out with on the reactant side of a reaction, we have to have the same number of atoms on the product side as well. So if I'm looking at this reaction on the reactant side, I have 2 times 2, 4 hydrogen atoms. So I better have 4 hydrogen atoms on the right-hand side or the product side. And so 2 times 2 gives me 4 hydrogens. I have 1 times 2, 2 oxygens on the reactant side. I have 2 times 1, 2 oxygens on the right-hand side. And so this equation, we call it balanced, which means that I have exactly the same number of atoms on both sides for each element that is taking part in the reaction. So let's talk about a little bit of how do we classify matter. Some of this, like I said, will be a review for you. However, these are simple definitions, so they can be learned very quickly. But we divide matter in 2 main divisions, so 2 main parts: pure substances, or mixtures. From the name pure substance, okay, so pure substances cannot be separated or purified into simpler components, and the composition does not vary. So it's the same throughout. Wherever I sample or I take my sample, the composition is the same. Now, they can be elements or compounds, and we'll talk more about what they are. So let's say I have sodium atoms or potassium atoms. That's a pure substance because they're not mixed with anything else. And I can't purify it into simpler components because I only have one. So I have one type. And if I take, let's say I have a bar of sodium metal, if I take a sample from the surface, it will not change in composition from a sample that if I drilled a hole and I took a sample at the core, the composition will not change. So the composition of a pure substance does not vary depending on where you get the sample. That's an example of an element that's a pure substance, but we can also have compounds that are pure substances as well, like water, for example. So if I have a jar of water and nothing else in it, so I have purified water, no minerals, nothing dissolved in it, then that is also a pure substance. It's not mixed with anything else, a different type of compound or a different type of element. It just has water. And whether I take a sample at the top or in the middle or at the very bottom, it should not vary in composition. Elements. Like I said, pure substances can be elements or compounds. Elements cannot be decomposed into smaller or simpler substances by chemical means. Elements are what fill up the periodic table of the elements. That's what we call it. And there's about 92 or so naturally occurring elements. Everything else is we have about 118 of them, but most of them are they're created in a laboratory. They don't naturally occur. And so elements are what populate the periodic table, and they differ from each other. So I can have sodium as an element, I can have hydrogen, I can have potassium, I can have calcium, copper. Those are all different elements and they differ from each other, and we'll talk a lot more about that more in detail. But they're not can't be separated or decomposed by chemical means. Compounds can be made up of two or more elements, just like we talked about the water molecule. Under the pure substances, you can have a pure substance that's a compound, and the compound is made up of two or more elements. And I can actually split the compound and decompose it or separate the elements. Now, it might take a lot of energy to do so, but it can be done. It can be split into its original elements. For example, I can take water and I can split it into the oxygen and hydrogen, which are the elements that make up the compound. We have millions and millions of compounds that are known to us, but the definition of a compound is that they're composed of two or more different elements. And there's a couple of examples here, like calcium chloride or sulfuric acid. So here's a picture of what each of these definitions look like macroscopically or microscopically, I'm sorry. So here, if these red balls represent the atoms of sodium, for example, that would be atoms of one element. And you can see that they're the same color, they're the same shape. If I take a sample over here or a sample over here, it doesn't matter. The composition does not vary because it's made up of the same element. Now, I could have molecules of a particular element. For example, oxygen is made up of the oxygen molecule is made up of two oxygen atoms, and it's not the only one: hydrogen, nitrogen, chlorine, fluorine, bromine, iodine. They're what we call diatomic molecules. And they're molecules because they're made up of more than one atom, but they're molecules of the same element, and they're pure substances as well because they're not necessarily mixed with anything else. So the difference between these two pictures, the red and the blue, the red represents only single atoms of one element. The blue represents a diatomic molecule that is formed from two atoms of the same element. So this could be hydrogen, for example, two atoms of hydrogen bonded together to form the hydrogen molecule, or oxygen, or any of the gases that I mentioned earlier, or the liquid. The next little pictorial here represents molecules of a compound. As you can see from the colors, we have different colors here representing different elements. And the definition of a compound is that it's made up of two or more elements. And you can see that by the color. I have two different elements, and actually four different atoms, but two types of elements. And then the last little image here is a mixture of all of those. Now you can see for these first three, they are pure substances, even though some of them are molecules of the same element, and the third one is a compound. However, the composition doesn't vary because no matter where I pick a sample, it's going to be the same one that makes up that um, the composition. And so it doesn't matter in the first three images, it doesn't matter where I sample, the composition is the same. And so they're all pure substances, pure substance of the atoms of an element. Pure substance in the second picture is pure substance of molecules of the same element. And then the third picture is pure substance of the molecules of a compound. The last picture, however, shows me a mixture. I do not have the same composition throughout. If I sample on the top left-hand side, I get an element, but if I sample on the top right-hand side, I get a compound. And so the composition varies depending on where I sample. So this is not a pure substance, but a mixture. So let's take a little closer look at mixtures. Mixtures are combinations of two or more substances that can actually be separated by physical means. This is important. We're not talking about chemical means here, we're talking about physical means. And some physical means that we use to separate mixtures can be distillation or evaporation. So if I have a mixture here of two different substances, that I can take advantage of the fact that they have different boiling points. And so one of them might boil faster than the other. And as it boils, I can force it to go through this tube. And as I cool this tube, it will condense and I can collect it in this flask. And that way it evaporates faster. And as it evaporates, it condenses down this tube and it's collected over here. So I can separate it from the other substance in the mixture because the other one will not be boiling yet. That is a distillation or evaporation apparatus. We've seen this in everyday life. So if I take sodium chloride or table salt and I dissolve it into water, if I just leave it on the countertop, what happens to it? We all know that eventually all the water is going to evaporate or leave the mixture unless you have a lid on, but if it's open, it will evaporate and eventually all you're going to have left behind is the crystals of the salt. In this case though, I'm not collecting the water, I'm just leaving behind the salt. in this apparatus, in this picture over here, we are collecting both parts of the mixtures. Another way that we chemists use is called chromatography, and it makes use of the fact that different compounds can travel in a medium differently depending on their size. And so I can then separate different mixtures this way. I'm not going to go into too much detail right now on it, but know that we have different ways of separating mixtures, and these are physical means, not chemical.